Okay, so here's the diagram I was talking about in the last video. I have two tanks, okay, tank A and tank B, and they are closed off with this valve right over here. Tank A, uh, the capacity is 5 liters, and in tank A we've got oxygen, and the pressure of the oxygen in tank A is 24.0 atmospheres, okay? In tank B, the capacity of this tank is 3 liters, and you've got nitrogen here, and the pressure of the nitrogen is 32.0 atmospheres, okay? If you open up the valve, what's going to happen? Remember, anytime you give a gas more space, it's just going to expand out. It's the same number of molecules of gas, but the distance between them is just going to get bigger, all right? So they just fill up whatever space they're in. So you're going to open this up, and now both gases are going to mix. So open the valve and allow the gases to mix. The question is, what's the partial pressure of the oxygen? What's the partial pressure of the nitrogen? And now what is the total pressure? Well, think about what's happening. Once you've opened the valve, you've changed the volume, right? What gas law is that? Where the temperature is still the same, nothing's happened to the temperature, but the volume has changed. And if you change the volume, what happens to the pressure? You change the pressure. So oxygen, when it was right here in the 5 liters, had a pressure of 24 atmospheres. But once you're going to open up the valve, now it's going to be floating in both valves. So the new volume is going to be 8 liters. And so what's going to happen to the pressure? It's going to go down, right? Because as you increase the volume, according to Boyle's law, the pressure will go down. So let's go ahead and do the math for that. And we'll first focus on the oxygen. Remember, it's P1 V1 equals to P2 V2, all right? Initial pressure was 24 atmospheres. Initial volume was 5 liters. Final pressure, that's what we're looking for. And then final volume was 5 plus 3, 8 liters. Okay? So you solve for the pressure of the oxygen here. Let's go ahead and do the math, manipulate the equation. 24 times 5, 24 times 5 divided by 8 is equal to 15 atmospheres. So the pressure of the oxygen is now 15 atmospheres. Okay, now let's do the nitrogen. Same thing. P1 V1 equals to P2 V2. What was the initial pressure of the nitrogen? 32 atmospheres. What was the initial volume of the nitrogen? 3 liters. Final pressure, we don't know. Final volume will be 8 liters because, again, opening it up gives you that whole 8 liters. All right, let's crunch the numbers. 32 times 3 divided by 8 is equal to 12. So now the pressure of the nitrogen is 12 atmospheres. So the question was, what's the partial pressures of each individual gas? We found the new pressure of the oxygen is 15, the new pressure of the nitrogen is 12. What's the total pressure? And this is where Dalton's law kicks in. So we use Boyle's and we're using Dalton's. Pressure of oxygen plus pressure of nitrogen. So you've got your 15 plus your 12, and you end up with 27 atmospheres. That is your new pressure. Okay? All right. I like this problem. It's pretty cool. I think the reason I like it is that you're using two gas laws in the same problem. So it makes it interesting. All right, the next problem we're going to do relates to what you guys are going to be doing in lab. In lab, you're going to have a piece of magnesium, and you're going to coil it and put it at the bottom of something called a eudiometer. And the eudiometer is like this tube that's closed off on one end. And that eudiometer, gosh, I am so not an artist at all. Anyway, that's even worse. That's okay. Anyway. You're going to put this eudiometer into, there's going to be magnesium right here. This is magnesium, okay? And you're going to put HCl right here. There's going to be HCl, and you're going to fill it up with water, okay? Then the HCl is going to start to come down, 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 and react with the magnesium. And this is water here also. So you've got magnesium reacting with HCl to produce magnesium chloride plus hydrogen gas. Because the magnesium is higher than hydrogen on the activity series, it kicks it out, hooks up with the chloride, and here's my balanced equation. Okay, where's the hydrogen gas going to go? It's going to bubble, 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 and start to collect in the eudiometer, okay? And it will displace the water. So this is hydrogen, and this is water. So the water will go down, and you will collect your hydrogen up here. And you will measure the volume of the hydrogen that you collect. The interesting part is that when you are trying to figure out the pressure of the hydrogen, you have to take into account that you also have water vapor here. Anytime you collect a gas over water, you have to subtract out the vapor pressure, the pressure of the vapor that is right here. Vapor pressure, by definition, is basically, I can give you the definition here. It is the pressure exerted by the gaseous molecules of the vapor in equilibrium with the liquid. So what you guys should know is that, excuse me, anytime you collect a gas over water, you're always going to get some water gas there, which is the vapor. And anytime you have a gas, that gas produces pressure. So the total pressure is equal to the pressure of the water vapor plus the pressure of the hydrogen gas. So in order to figure out the pressure of the hydrogen gas, you do the total pressure minus the vapor pressure. Well, how are we supposed to know? How are we supposed to know what the vapor pressure is? There's actually a table in your book and in your lab manual that gives you the vapor pressure at different temperatures, okay? So you're going to be taking the temperature of the water, and you're going to look up the vapor pressure at that temperature. All right, so let me show you what a problem, very similar to what you guys are going to be doing in lab. And you could also get something like this on an exam and obviously in your homework. So here's the problem. I have something in my throat. Excuse me. A sample of hydrogen was collected over water. Sometimes the lingo is by the displacement of water or collected over water. Anytime you see that, you know that you're going to have to subtract out the vapor pressure to get the pressure of whatever gas you're collecting, okay? So a sample of hydrogen was collected over water. The hydrogen occupied 742 milliliters at 27 degrees Celsius. The barometric pressure. So whenever they say barometric pressure, that's the total pressure. The barometric pressure, or atmospheric pressure, barometric pressure was 753 millimeters of mercury. What volume would the dry hydrogen occupy at STP? Okay, so several things are involved in this problem. All right. We're going to have to subtract out vapor pressure in order to do anything with the pressure that they give you. So remember how I told you guys that total pressure, which is barometric pressure, is equal to the pressure of the hydrogen plus the vapor pressure? Pressure H2O is vapor pressure. So the first thing you want to do to figure out the pressure of the hydrogen is you have to take your total pressure and subtract out the vapor pressure. You have to subtract out the vapor pressure. So we're going to look up the vapor pressure at this temperature, at the temperature of 27 degrees. And in the chart, it says 26.74 torr, or millimeters of mercury. So I'm going to go 753, which is the total pressure, minus the vapor pressure. Always subtract out vapor pressure when they collect over water. So we're going to subtract out 26.74. And you end up with 726 millimeters of mercury, or torr. So this is going to be the pressure of the hydrogen gas. That's the pressure of the hydrogen gas. All right. We haven't done very much. We just figured out the pressure of the hydrogen gas. All right. What do they want from us? They want the pressure, the volume of the dry hydrogen. Dry hydrogen just means make sure you subtract out vapor pressure. So whenever they're asking for dry anything, it's after you've subtracted out the vapor pressure, because the vapor pressure makes it wet. Okay? They want it at STP. We are not at STP. We are at 27 degrees Celsius and 726 millimeters of mercury. So they want V2. So really, this problem, you could approach it two ways. You could do an ideal gas law, get your moles, and then once you get your moles, do standard molar volume to get your volume, or do combined gas law. Let's go ahead and do both techniques, okay? And we should end up with the same answer. I'm going to erase all this to give myself some space, but hopefully you've written down the problem. And let me just show you how to do this, okay? Because this is exactly what you guys are going to be doing in lab. All right. So combined gas law was P1V1 over T1 equals to P2V2 over T2. I have my pressure of the hydrogen. So I'm going to write 726 millimeters of mercury. My volume that I just measured is 742 mils. 742 mils. My temperature was 27, so that's 27 plus 273. Remember, anytime you do any gas law, you got to use temperature in Kelvin. And then P2 is STP, which is 760. V2 is what we're looking for. And then T2 is STP 273. Okay, so crunch the numbers. Let's get our calculator. 273 times 726 times 742 divided by 760 divided by 300 is equal to 645. Yeah, that looks fine. 645 milliliters. 645 milliliters. Using combined gas law. Let's now go ahead and do ideal gas law. Let's see if we get the same results. We should get something very similar. So we're going to do PV equals nRT. We're going to solve for N. All right, so we're looking for the pressure that we just figured out was 726. 726, we're going to divide that by 760 so we can get it in atmospheres. The volume was 742 mils. We're going to turn that to liters, 0.742 liters. N is my unknown. R is 0.0821. And temperature is the 27 plus 273, which is 300. Okay, so we're going to solve for N. All right, 726 divided by 760. Everybody knows why I'm dividing by 760. Because you need it in atmospheres, right? And then times 0.742. And then we're going to divide by 0.0821. And then divide by 300. Okay, so we got moles, 0.0288 moles. All right, now we're going to use STP. 0.0288 moles. For every 1 mole, it's 22.4 liters. Let's multiply it by 22.4. And yep, you get 645. Yep, 645 milliliters. It's 0.6446 liters. So same thing, 2 methods to get the same answer for collecting, figuring out the volume at STP once you've collected gases over water. All right, we're going to go through this in lab, but at least now you know how to do it. Okay, and then we probably have just one more video and we'll be able to wrap up this chapter.